Hi everyone, and welcome to L2V2 Graphical Analysis. This is our second video for Lesson 2, and it focuses on examples that you might see in an assessment. In your maths classes, you learned about linear graphs, and you know all about the y equals mx plus c formula. In our physics classes, we apply what we learn in maths to help us solve problems and find answers. In this video, we want to refresh our memory on how to create a scatter graph. We want to provide an example on how to manipulate data in accordance with a supplied relationship so that you can make a linear scatter graph. And we want to give examples on how to find the gradient of linear scatter graph and the y-intercept of a linear scatter graph so that you can solve problems and find answers. Here is an example of a scatter graph. You'll be required to draw scatter graphs with lines of best fit in pretty much every exam you do from now on. Semester 1, Semester 2, Year 11, Semester 1, Semester 2, Year 12, and also in your WACE exam. In an exam that's usually got about 180 marks, these scatter graphs, just the drawing of them, is usually going to be worth about 4 marks, maybe 5 of that total. As you draw more scatter graphs, you'll get better at the selection of scale on the x and y axes so that you can use the full space allocated for the scatter graph. You will get marks for accurate plotting on the scatter graph. You will get marks for including a line of best fit, and you will get marks for axis titles and also axis units. And then, in a graphical analysis question, when you are asked to find the gradient, you will get marks for showing evidence on the graph that you used particular coordinates on the line of best fit, and this evidence will often take the form of lines drawn in to find the rise and run of those particular data sets. When you look at the equation y equals mx plus c, it is important to remember that the y and the x parts of the equation are variables, while the m and the c parts of the equation are constants. The m part of the equation is the gradient, and the c part of the equation is the y-intercept. So for y equals mx plus c, we have 2 variables. And we place those 2 variables on either side of the equals sign. When we are given data that doesn't create a linear graph, for example, the marble data we had from the last video, data which includes time and distance data for a marble falling from a hot air balloon. When we are given data that doesn't match the linear shape, and when we are given an expression that ties the 2 data sets together, for example, s equals a half at squared, one of the first things that we must do is identify that part of the given equation, s equals a half at squared, which are the variables. If we lay the equation y equals mx plus c above the equation s equals a half at squared, it makes it easier for us to see which parts of the equation are variables. The distance part of the equation, s, is a variable, and that's on the left-hand side of the equal sign, and it coincides with the y part of y equals mx plus c. The time, t, part of the equation, s equals a half at squared, is also a variable, and is on the right-hand side of the equal sign, and falls underneath the x part of y equals mx plus c. So we have a variable on the left, that's distance, and we have a variable on the right of the equal sign, that's time. But if you plot distance against time, you will not get a linear graph, so you have to manipulate the data. The equation s equals a half at squared tells us how to manipulate the data. If we take the time data and we square it and plot the square of the time data on the x-axis and the square of the distance data on the y-axis, then we should be able to get a linear graph. Let's do an example. Example 1 is taken from West Australian Test Papers Semester 2 paper for 2022. The background theory behind the example is not really that important. All that matters is that we have activity data, that's radioactivity data, represented by A subscript D in microbecquerels, and we have distance data, which is in meters. The background theory for this example is to do with nuclear physics, and it talks about the readings taken from a Geiger counter at different distances from a radioactive source. If we were to graph the raw data presented here with the activity data on the y-axis and the distance data on the x-axis, we would not get a linear graph. So we're going to need to manipulate the data in some way. We are given the equation AD equals 0.00007162 A subscript S over R squared. AD is the activity measured, the radioactivity measured by the Geiger counter at some distance R from the radioactive source. AS is the actual activity of the radioactive source, and R is the distance between the radioactive source and the Geiger counter. The thing about Geiger counters is that they can only read the radioactivity that is directed towards them. So the further you get away from a radioactive source, the less of the activity that the Geiger counter is going to read. The radioactive source is letting out radiation in all directions surrounding itself, but only that radiation which is targeted towards the Geiger counter is going to give a reading. In any case, we have data and we need to manipulate the data. We're given an equation, which you see on the screen, so we have to rearrange that equation into the shape that fits the y equals mx plus c structure. We can look at the equation and we see that there are two variables in the equation. A subscript D is the variable that's the activity read by our detector at different distances, and the distance from the source labeled R is a variable. These two variables are already located, one on either side of the equal sign. So in order to make this look like a y equals mx plus c equation, all we've got to do is take the distance data, square it, and find the inverse of it. This is easier to see if we color code the two equations. The target equation, y equals mx plus c, which is the linear equation, color coding that one, and then color coding our given equation, AD equals 0.00007162 AS multiplied by 1r squared plus 0. In our supplied equation, we have A subscript D, the activity of the detector. We're going to plot that data on our y-axis. You'll notice that in my color coding, it's red and the y is red. We have the distance data color-coded in yellow. We're going to plot that on the x-axis, but before we plot it on the x-axis, we're going to square each entry in the distance column, and we're then going to inverse the square of each entry in the distance column. So we take the raw distance data, we square it, and we find the inverse of it. We go back to our raw data table, we take each of the distance data values, we square it, we inverse it. We remember also in our new table, our manipulated data table, to put in the title at the top of the new column, and the title is going to be 1 over r squared. And remember to put in the units for that column, which is going to be meters to the neg2. Units are really important in physics. Now, having manipulated the data, we plot activity for the detector, A subscript D, on the y-axis, and we plot on the x-axis 1 over r squared. And we make sure that we title the x-axis the inverse square of distance, and we give the units to the x-axis as meters to the neg2. Having manipulated the data and having drawn the linear graph with the correct titles and units on both axes, we now have to find the gradient of the line of best fit of this linear graph. You'll remember from your maths classes that to find the gradient of a line, you say the gradient equals rise over run. For us in physics, we can see that the rise is 26 minus 2, but we must always remember in physics that it's not simply 26 minus 2, it's 26 minus 2 microbecquerels. The units matter. The run, according to us in physics, is 100 minus 8 meters to the neg 2. Again, the units matter. We get out the calculator and we find that the gradient is equal to 0.261 microbecquerels meters squared. Having found the gradient, we go back to our given equation and we see that the part of the equation that was the gradient is 0.000076162 a subscript s. On the screen, you can see that as the green part of the equation. So now we know that the equation becomes 0.0007162 a subscript s equals 0.261 microbecquerels meters squared. All we have to do now is solve for a subscript s. Remembering that a subscript s is the activity at the source, the total activity from the radioactive material. And we find that it's equal to 3,662.6 microbecquerels meters squared. The last thing we do is we give our final answer, seen here in yellow. The activity at the source is equal to 3,700 microbecquerels. We give our final answer to two significant figures because we cannot claim any greater precision than this from a graphical analysis. We give our final answer as 3,700 microbecquerels. We've dropped off the meters squared because at a point r equals 0, in theory, there is no surface area through which the activity is being released. Or rather, the surface area of the source is the activity through which it's being released. Either way, that isn't something we worry about in Year 11. Let's look at example 2. This is taken from the West Australian Test Paper, Semester 1, 2019 paper. This is an electronics question. You don't need to know anything about electronics. We're just going to look at the raw data and then use the supplied equation to manipulate the raw data in order to find a linear graph, and then use the linear graph to find some quantity that is of interest. You may remember from Year 9 science that some materials have a resistance to the flow of electricity, and that this resistance is linked to a physical property called resistivity. In this question, we're trying to find the resistivity of a conducting putty, which can be molded into cylinders of different length but with fixed volume. We're supplied with raw data for the length of the cylinder and the resistance of the cylinder. This raw data, unfortunately, does not give us a linear graph though. But don't worry, we are supplied with an equation. Resistivity, ρ, is equal to R minus R naught, all in brackets, multiplied by volume, divided by L squared. So let's walk through that. Resistivity, ρ, on the left-hand side of the equation. That's a Greek letter ρ. That's a constant. On the right-hand side of the equation, we have our first variable, resistance, R. Subtract R naught. R naught is the resistance of all the wires involved in the experiment, and that's a constant. We have another constant, volume of the putty, which will always be the same throughout each trial. And that's all divided by L, the length of each different cylinder squared, a variable. We have constants in the form of resistivity. That's a constant. That's actually the constant we're hoping to figure out. We have the constant R naught, which is the resistance of the connecting wires. That's a constant. Doesn't vary throughout the experiment. And we also have the constant in terms of volume of the conducting putty. Looking again at the equation, we have variables. We have two variables. There's the length variable, which we can see in this equation, is in the denominator, and it's squared. That's the length of the putty cylinder for each trial. And then there's the resistance variable, the resistance of the putty at different lengths, and that's in the numerator and inside the brackets. Both of our variables are on the right-hand side of the equals, though. So one of the first things we're going to have to do is rearrange the equation to more closely match the style of y equals mx plus c. In this slide, you can see we're rearranging the given equation step by step to more closely fit with the style y equals mx plus c. We take the L squared part of the equation first, we multiply that out to the left. Then we take the volume part of the equation and we divide that over on the left. And we end up with rho L squared on V equals R minus R naught. Finally, we isolate the resistance part of the equation. And we end up with R, the resistance of the putty tube, is equal to rho on V multiplied by L squared plus R naught. And you can see already by the color coding I've been putting in here, we've got red for the R and we've got yellow for the L squared. Now that we've made the given equation a bit more closely matched to the target equation of y equals mx plus c, we can determine how to manipulate the data. We will leave the resistance data exactly the same, and we'll be plotting that on our y-axis. But we'll take the length data, which you see here in yellow, and manipulate it by squaring each value of the raw length data that we've been given. So we go back to our original data table, we take all of the length data in centimeters, and then we square the length data. So 6 centimeters becomes 36 square centimeters. 11 centimeters becomes 121 square centimeters. We make sure that our manipulated data column is titled appropriately, length squared, and given the appropriate units, squared centimeters. We take the manipulated data, we plot resistance on the y-axis, we plot length squared on the x-axis. We make sure to give the appropriate titles of each of those axes, resistance with the units ohms on the y-axis, square of length with the units centimeters squared on the x-axis. We put in a line of best fit, and we find the gradient of this line of best fit in the usual fashion using rise over run. Now, you can see in this screen that I've cheated because I've just allowed Excel, the program, to give me the gradient of the line, and that comes up to be 0.579 ohms per squared centimeter. Once I've found the gradient of the line, I then go back to my given equation, R equals rho on V L squared plus R naught, and I can see that the green part of that equation, rho on V, resistivity on volume, is the gradient part of the equation. So I bring that into my calculation. Rho on V equals 0.57 ohms per square centimeter. I plug in my volume, which from the question is 15 cubic centimeters. I multiply everything out, isolate for resistivity, that's rho, and I end up with rho is equal to 8.68 ohms per centimeter. I give the final answer as 8.7 ohms per centimeter because I don't want to give an answer that is more than 2 significant figures, because that would be claiming a precision that I have no right to claim in a graphical analysis. So there you go. We've got 2 examples of graphical analysis in this video completed. That's the end of the video. What now? Take a moment to jot down ideas from this video in your physics notebook. Try to do it from memory, don't go back and copy it out word for word. Then, read and take notes on Appendix B of your Pearson Physics 11 text, if you haven't done that already. Complete Chapter 1.3 questions from the PDF titled HB Chapter 1.1 to 1.3. You'll find that in Sector. And if you've done all of this, complete the exit ticket for L2 graphical analysis. Hand it in and get ready to do L3, where we begin talking about thermal physics. I hope this was useful.